Welcome. This short tutorial will illustrate how to use the link elements available in AxisVM. The tutorial is based on a semi-composite layered timber beam model and assumes the user has AxisVM modeling experience with rib finite elements. Floor-to-wall connections can be modeled similarly. The composite member consists of two wood layers interconnected by multiple connectors or an adhesive that provides interlayer force transfer. Each layer has to be modeled separately along their own axis using rib finite elements. The bottom layer has a 20 by 40 centimeter cross section and the top layer is 20 by 20 centimeters, both made up of Douglas fir timber. Since the line-to-line link elements, which are 2 by 3 node distributed spring elements, are intended to be applied to the model for the interlayer connection modeling, the beam members of the two layered structure should be modeled by rib elements, 3 node beams. The line-to-line link elements modeling the interface have 6 stiffness components. In this example, the local system of the line-to-line links is parallel to the global coordinate system. The interface is located at a ratio of 2/3 with respect to the master nodes at the bottom. In this case, the horizontal slip stiffness, Kx, is provided by the line-to-line link elements, uniformly distributed over the length, and its value is usually based on experimental investigations, being slip tests. A 0 Kx value would result in non-composite behavior, which is not the case here since there are a number of connectors installed. A 0 value would also introduce a rigid body mechanism since the two layers would allow the two wood members to slide on each other. Therefore, to avoid such a singularity, a finite low value should be entered even in the cases when non-composite behavior is desired. An infinite or very large value would result in fully composite behavior. Otherwise, the behavior will be semi-rigid. The Kz value should be very large to ensure the conform deformation. A mesh of 0.3 meter size finite elements is then applied to the beam. The composite member is simply supported. A pin support is defined to the left and a roller support is applied to the right end of the beam. Since the XZ global plane was chosen for this 2D model, the degrees of freedom of all of the nodes will be constrained according to a frame in XZ plane setting. A mid-span point load is also applied to the model. Then a linear static analysis is performed and the deflected shape of the beam will be displayed first. Due to the composite action, axial forces develop in both layers, compression on the top and tension on the bottom, along with a bending moment and associated shear force. The diagram of the NX component developing along and in the link elements shows the variation of the shear force in the connection. In conclusion, by varying the horizontal slip stiffness component of link elements, the non-composite, semi-composite, and full composite multilayer beams can be studied. Thank you for watching. Additional information and tutorials on the modeling capabilities of AxisVM are available on the AxisVM website.